Hello and welcome back to my YouTube channel. So in last lecture we have seen, or in last video we have seen, the deflection and slope of the beam when point load is acted on the beam. Today we will see the relation between slope, deflection and radius of curvature. Clear? So for that purpose I have considered here AB is one of the beam. So here I have considered this is AB is the beam and it is deflected over here, and in AB I am considering some portion, so that portion is PQ. So here if you observe, this portion is PQ. Now it is having the length DS. So along x-axis I will consider, and along y-axis, I will consider dy, and along x-axis I will consider dx. Now small portion I have considered PQ in deflected beam. Now here I am considering psi angle which is making at the tangent at point P, and at point Q it is making angle psi plus d psi. Clear? So let the curve AB represent the deflection of the beam. So you might have seen earlier video also. If you observe this one, this will become radius of curvature, CP, CQ, or you can say AC or CB. So all is nothing but it's a radius of curvature. So here I can write PC, or you can say QC equal to the radius of curvature. Simple. Now if you observe this small triangle, so here I will draw the triangle in large view. So this is PQ, this is a dx, and this is dy. Simple. Now as I am considering this is psi, so definitely this will become psi, this angle. So line is same, horizontal line, this horizontal line same, so this angle you can say this one is a psi. So here I am considering this angle is a psi. Now from that I can say this PQ is nothing but is a ds. So if I write for ds, then I can say r into del psi. Clear? So r into del psi. Here if you observe, this is the nothing but is a radius of curvature, and this angle is del psi. Clear? So if you want to know the arc or radius of arc, then sorry, distance of arc, we can say r into del psi. Clear? Now you might be thinking that, sir, how this angle you have evaluated del psi. So for that purpose considered I have considered same figure in two diagram over here. So let's say this is the psi angle. If I draw vertical line, as you know, this is 90 degree. Can I say this is 90 minus psi? Yes. Simple. Now if I draw one horizontal line here, if I draw horizontal line, so can I say this is psi? Yes, this is again psi, as we have already considered 90 minus theta. So I will check the chalk, change the chalk. Now if you observe, this is a tangent. Clear? So can I consider this is 90 degree? Yes. So as this angle is psi, so this will become 90 minus psi. Simple. Again I will change the color chalk. So if I drop a vertical line from this, so can I say this is 90? Yes. To this horizontal line, this is 90. As this is 90 minus psi, so can I consider this is psi? Yes. Simple. Likewise if you do for this also, so if you draw vertical line, so this will be the 90. Clear? So what will be this angle? This angle will be the 90 minus psi plus del psi. Simple. If you draw one horizontal line, so which we have, sorry, this angle we have evaluated, that is 90 minus psi. So we can say this is 90, this is also 90. Clear? So I will say this angle, this is 90 minus psi minus theta, this is 90. So this angle, what will be this angle? This angle will be the psi plus del psi. Simple. Now if you observe this angle, then I can say OQ and Q, let's say this is X, QX, both are perpendicular to each other. So this is psi minus, sorry, psi plus del psi. So this angle I can write 90 minus psi plus del psi. Clear? If I consider this is 90 minus psi plus del psi, and if I drop one vertical line, so this is 90. So can I consider this is psi plus del psi? Now from this equation we already seen that this particular angle up to P, this is psi. So what will be this angle? This angle will be the del psi. Psi minus del psi is, and this entire angle. Clear? And this one is a psi. So I can say del psi. That's why this angle become the del psi. Clear? So from that, can I consider del S equal to R into del psi? Simple. So I will write radius of curvature, that is nothing but it's a del S divided by del psi. Simple. Now come to the next part of the discussion. I will consider again the same triangle which we have already considered, that is this is DCS, this is P point Q, dy and dx, just this one. Clear? Now we already seen that this angle is nothing but it's a psi angle. Clear? So from this angle I can evaluate some angle, that is tan psi. So what will tan psi? Dy divided by dx. If I consider sin psi, then that will be dy divided by ds. Then cos psi, that will be also equal to dx divided by, sorry, yes, dx divided by ds. Simple. Now if you divide equation 1 by dx, then I will consider this is equation 1, ds divided by del psi. If you divide this equation, so I will rewrite r is nothing but it is equal to ds divided by del psi. Is it right? Yes, ds divided by del psi. So divide this equation by dx. So I can write r equal to ds divided by dx divided by del psi divided by del x. Clear? So from this equation, if you compare this equation, what is this? Dx divided by ds. Here we want, what we want? Ds divided by dx. So can I say 1 by cos psi? Yes. Then that will be 1 divided by cos of psi divided by del psi divided by del x. So what is 1 upon cos psi? That is a sec psi divided by d psi divided by dx. Simple. So let's say this is equation number 2, this is equation number 3. Now if you differentiate equation with respect to x, then what will be there? Let's see. Wait, I'm just adjusting. So if you differentiate this equation, then we can say sec square psi equal into del psi divided by del x equal to del 2y divided by del x square. Sorry, equation 2 is tan. So this is equation number 2, please pardon me. So what is differentiate of tan? Sec square into del psi divided by del x equal to differentiate of this dy by dx, that will be the d2y by dx square. Simple. So I will write del psi divided by del x equal to del 2y divided by del x square into sec square psi. Why I have taken differential of equation number 2? Because what we want del psi divided by del x. Clear? That's why we have differentiated over here. Clear? Now just I will substitute this all value in equation 3, sorry, equation 3. So this equation will become radius of curvature r equal to sec psi divided by del 2y divided by del x square into sec psi square psi. So here if you observe, by rearranging, this will become sec cube psi divided by d square y divided by del x square. Simple. Now I will take reciprocal of this both the side, then I can write 1 upon r equal to d2y divided by dx square divided by sec cube psi. Simple. Now just I'm using the simple term, that is instead of sec cube I can write says sec square psi, and I can take 3 out of the box. Clear? So what I did, I am just taking sec square, but I am taking this 3 outside, and again I will divide by 2. Simple. Why I am taking this, you will get to know over here, because sec square psi is equal to the tan square psi. So 1 by r, that will be equal to d2y divided by dx square divided by 1 plus tan psi raised to 3 by 2. This is tan psi raised to psi. Now in this equation, if you observe, there is a tan psi. However, again what we are looking for, we are looking for this for the practical application. Now again the angle, or we can say slope tan psi at any point is small quantity. So what we will do, we will neglect it. Clear? So from above equation I can rewrite the equation 1 upon r equal to d2y divided by dx square. Clear? So let's say this is equation number 4. Now again we will use our bending moment equation, m by I equal to e by r, and for r I will write m by ei. Just put the value in above equation, then we can say 1 upon r, sorry, 1 upon r equal to m by ei. Just put in above equation, so I can say m by ei equal to d2y divided by dx square. And if I write for moment, then this will become ei into d2y divided by dx square. So this is equation for the bending moment. Now differentiate above equation with respect to x by taking differentiation with respect to x, then I can say moment divided by del x equal to ei, as this is constant, so I will consider ei into d cube y divided by dx square. Now here we can say dm divided by dx, that is nothing but f, and this is nothing but it's a shear force. Clear? So we can say that shear force, it will given by equation ei into d cube divided by dx cube, sorry, it's a cube, as dx square we have taken differentiation. Clear? Again we will differentiate above equation, differentiate with respect to x, then we will get df divided by del x equal to ei into d raised to 4 divided by y, sorry, d raised to 4 y divided by dx raised to 4. Now df divided by dx, what is this? This is nothing but rate of loading, or we can denote it by small letter w also. Clear? So from this above relation we can rewrite the relation between the deflection and slope. Here I can write, if deflection is y, and then slope will become theta will be equal to dy by dx. Clear? So next is bending moment m, so that will be equal to, we have derived ei into d2y divided by dx square. Where we got this? Here, this is bending moment. Clear? Where is the slope we can say dy by dx. We can take tan theta from above triangle. Here this triangle, tan theta equal to dy by dx, or that is equal to theta also. Next is shearing force F equal to ei into d cube y divided by dx cube. And next is rate of loading, that is w. Here you can write ei into d raised to 4y divided by dx raised to 4. Simple. So in above equations it will give the relation between the deflection, slope and bending moment. Here we can have the equation for shearing force as well as rate of loading. Now there are different methods are there for determining the slope and deflection at any section. Clear? So methods are there, so I will write the name only and we will discuss it later on. So first method is double integration method, through which we can evaluate the deflection and slope and bending moment at any section. Second method is moment area method, and most important method is, and simple method we can say, that is Macaulay method. Clear? So in double integration method also, what we will do, we will use same equation that is we have derived, that is bending moment equal to ei into d2y divided by dx square, or we can say d2y divided by dx square, that will be equal to m by ei. So first integration of this particular equation, first integration of above equation will give the value of dy divided by dx, and then what is this? This is nothing but it's a slope. And if you take again integration, then it will give the equation for y, so that is nothing but it's a deflection. So what we are doing? We are doing the double integration. That's why it is called as a double integration method. Clear? So first, these two methods are used for single load. Single load. If multiple loads are there, then we will go to the Macaulay method. I hope you understood the entire derivation along with the relation between slope, deflection and beam. Thank you.